Okay, good morning, everyone. I hope you are doing all right. So last class, we did not quite finish the slides that we had planned to finish on that class. So I'm starting from right there. So towards the end of the class, we talked about conservation of angular momentum, which means total final angular momentum is equal to total initial angular momentum, provided that net torque is 0, and the angular momentum is defined as rotational inertia times angular velocity. So those are the things that is about the angular momentum. So this is conservation of angular momentum. So we talk this in terms of like how figure skaters, basically they bring their hands in the closest possible towards the end of the their act. So why do they do that and so on? So we talked about that, and here is question about exactly that. So let's see what you remember. So you have 1 minute and 30 seconds to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see. How did we do? So mostly the angular velocity increases because our rotational inertia decreases, yes. So that is correct answer. So if we write that, something like rotational inertia final times angular momentum final, angular velocity final is equal to the total initial angular momentum. So the final angular speed, what happens to the final angular speed? So rotational inertia, for example, being sum of all the masses in R square. So bringing R smaller makes I smaller. So R is smaller means I or rotational inertia are going to be smaller. Okay, so here we're talking about final situation. So that means it is smaller means this is larger. So at the beginning, when rotational inertia initial was larger, angular spin was smaller. Okay, so that is the essence of conservation of angular momentum. And if you need, write down this. You will be using this in next slide to compute the problem. Okay, so here is that question. So ice rink network 0 or at least negligible. Arms and legs fully extended. So initially that's what they are doing, right? And then brings closer to the body. So I'm just describing that situation there. So what is the final angular speed? If initial angular speed is 2 radian per second. So this is initial. So you see for the rotational inertia unit is written as a kilogram times meter square. So that comes from this definition here. So yes, we may put summation sign, but still it's the sum of mass and the radial distance squared. So that's why the unit for mass is kilogram, distance is meter. So the unit of rotational inertia is kilogram meter square. So that's what you see. So now that is the first part of the question. So can you calculate? So I'm giving you 2 minutes for this computation. Okay, so I made clicker question. So rather than typing on the chat, you can wait until I open the clicker. So now you have 1 minute and 30 seconds to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly C. I believe that is correct. Let's see. So IF omega F is I omega I. So that means omega F is, oh, yes. So I omega I over IF. So IF is, sorry, II is 4, omega I is 2, IF is just 1. So because of that, it becomes 8. Okay, so that is great. So now we have a second part in this question. Is energy conserved? So usually energy should conserve, but if some is dissipating, then we may not get total before and after, right? And so what it is asking is final is equal to initial. So what kind of energy is involved here? So this portion is just spinning in a place. So let's say no translational motion. So that means half mv square is 0. Similarly, height is not changing. So mgy, mg delta y, or mgyi, mgyf, both of them are same. So that means it's going to be 0 if we choose reference right there. On the floor. So that means total final energy possibly is half mvf square plus half I omega F square plus mgyf. So this we can say 0 because we are choosing reference right there where the person is doing the act. So height before and after remains same because person is still on the ground. Okay. So person is, let's say, not translating, doing this at the same place. So that's why this velocity is also 0. So EF is just half IF omega F square. So you can plug in number and get the number here. And similarly, EI, so I'm not writing all these, rather I'll just write. So rotational kinetic energy is relevant. Okay, so you can plug in numbers and get the answers. Since we already had omega F as a 4, right? So that's what we found. So that means we have all these. So you can do the computation. So most likely the number's not going to come out exactly equal. I don't know. I haven't done the math. So II is 4 and 2 square means 16. Half is 8, looks like. And for this one, IF is 1 and omega EF is 4. So 16 and half looks like they are basically same. So since we are assuming no friction, network is 0, it's not taking account of any energy dissipation. So there is no energy dissipation. That's what happening, assuming that there is no friction. So it looks like both of them come out to be like 8 joule, 8 joule. I just eyeball them, so you want to carefully check that, okay? So that is about the value of angular momentum. And how about direction of angular momentum? So angular momentum is defined as, oh, not I, but omega. This is scalar. This is vector. So that means direction of L is same as direction of angular velocity. So angular momentum and angular velocity, they have same direction. Just like linear momentum and linear velocity, they have same direction. Same thing goes with this because here this is scalar and here mass is also scalar. To describe mass, we don't need to tell 2 kilogram to the left or right, up, down. We don't need that. Similarly, rotational inertia is also scalar quantity. So that means direction comes from this. And in this sketch, that's what it is trying to show. It has a video, so that's why I brought it. So the angular momentum and angular velocity, they have same direction. So here, what you see, there is this wheel that is spinning this way, okay? So here, it's saying, okay, this is in that direction. So it's like if we have wheel like this, and if this wheel is spinning like this, the direction of angular momentum, actual physical direction, gonna be in that direction towards you if it is spinning like that. And if it is spinning all the way around, then the direction gonna be that. So the positive and negative we write, that's for just mathematical purpose, right? Assuming clockwise, counterclockwise, negative versus positive. But actual physical direction is, so it is perpendicular to the plane of this wheel. if this wheel is spinning, if something is spinning, the angular direction of angular velocity and hence the angular momentum gonna be either that direction or that direction, means perpendicular. If you see this ring sitting on the piece of paper, let's say if you are looking at this on the, let's say this video on the like device that's sitting on the table, that means it's sitting flat on the table, right? Something like that. So direction gonna be either down or up, and whether it's down or up in that case, see, that's the perpendicular to this plane. So whether that's down or up depends on which way it is spinning. So in this video, that's what it is trying to show you. So let's pay attention and watch.
And we're gonna rotate. Take our fingers, curl it around. The rim is moving in this direction. Point our fingers in the direction it's moving. So our thumb points up.
So that's how you do that. Use right hand, right? It must be right hand, not the left hand. Okay. So this is spinning this way. So when you curl your forefinger, so you start by stretching your hand like this. And when you curl in that direction, what happens? So see, the thumb and the fingers, they have to be 90 degree. So you curl the fingers and then thumb points in the direction of angular velocity or angular momentum. So that's what it is saying.
In fact, the vector of concern is always perpendicular to the plane, right? The plane of rotation. So the angular velocity vector points, in this direction of the spool here, right? Okay. And of course, that's the direction, the same direction as the angular momentum because L equals I omega. Okay. All right. And let's do another one. Let's do this one. Let's turn it back in the other direction. Curl our fingers in the direction of that, and our thumb points that way. And so that's the convention for. And we're.
So when we say vector has just the, like let's say, when we say vector has both value and direction, it's not just, for writing positive and negative sign, but it has actual physical meaning. And it has actual physical direction. And there is this another video. There is some demo going on. Let's watch and see if you can figure out what's going on and see if you understand. Okay.
And you're gonna pull the weights in. You don't have to do it really quickly. You just pull them in. All right. I won't go too fast, so feel comfortable. Okay. Now pull them in, and then back out again. So conservation.
So that is like a figure skater doing the, a trick, right? So starts with masses far, so R larger, I, let's say initial R larger, initial momentum, initial rotational inertia larger, right? Maybe I should have written somewhere on this side here.
Hang on.
Smaller because see how this person brings the hand right there, right?
All right, now I'm gonna need someone's help for the second part. I got it. So you sit in the chair the same way. Yep. You're gonna be holding this wheel. You could do it, so I would probably do it like this, so both hands in this direction. I'm gonna get it spinning, and then you're just gonna rotate it. Essentially, eventually all the way upside down, okay? So hold that, I would hold it that way probably. Are you comfortable in the chair? Yep. All right, I'm gonna have you hold the shoulders, because I'm gonna have to, just to get this rotating. And I won't have to go too quickly, because it gets really hard to move. You got him? Okay. Easy. Actually, that's fine. Okay, let go. Now rotate the wheel. Go all the way over. You should stop again, because now all the angular momentum is in the wheel again. So, sure, and then go all the way up, and then, yeah, I'll just. Yeah. Anyone else want to try?
Okay, on the second part, what happened? Did you get that?
On a chair, and you're gonna pull essentially, eventually all the way upside, just to get this rotating.
So when it is, let's see which way it's spinning.
It's really hard to move. You got him? Okay. Easy.
So it looks like it is spinning like that. Okay. So it is spinning that way when you look from the top, from top. From top. When looked from the top, spinning. How? Let's see. You look from there. So you look from the top there. It is spinning. So let's see. Video versus what I'm looking at. That may be. So it's going from the top. It is going. Let's say it's going that way. Means when I look from there, it's going counterclockwise. Okay. So when that's the case, what is the direction of? So I'm giving you choice here. Up, down, clockwise, counterclockwise. So I'm opening the poll and go ahead, poll on it. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So what did we get here? So up, down, or counterclockwise. And so here, when it is spinning something like that, angular momentum going to be always perpendicular to that plane. So it's going to be either up or down. Okay. So that's why this is not going to be correct. So now if to see if that is, like up or down. So based on if it is going something like that, then it's going to be pointing up using the right-hand rule. So it looks like up is the correct answer in this case. But when you are watching me here through the video, it may be a little bit confusing in terms of direction. So that's why you want to try on your own by curling finger in the counterclockwise direction and see what's going on. Okay. So now what happens here? So right now the wheel is spinning, the portion is not rotating. But once this tilted, what happens is that how the direction of angular velocity and angular momentum was in that direction beginning. So now it goes like that. See, it's changing. So direction of angular momentum changed here. So before all the angular momentum was, pointing up. So now it's pointing part this way as well. So since the angular momentum is conserved, what happens is so in this case, actually what happens is angular momentum changed, angular velocity changed, means the direction of torque also changes. So that means now the torque acts on the system here, the person sitting on the chair, and then it starts making it rotate. But when this person, like flips down and then flips back up, what happens? Person totally stops again. See that?
All the way over. You should stop again because now all the angular momentum is in the wheel again.
So it comes back to the original situation. Okay. So that is kind of interesting. See, only what changed here? Only the direction changed. So that's why direction is very important in terms of talking about this. So in this space, like when we send, let's say there are, so right now there is James Webb Telescope that is in this space, and there is also Hubble Space Telescopes, okay? So there is this telescope, and what you have to do is you want to point that telescope in a particular direction, right? And then fix that for a day or so. You don't want that to be rotating, okay? So to take the picture of galaxy or star, whatever you are interested in. So in that case, it has to be fixed there for a long time. So what happens is, since this thing, so they have mounted this in what's called a gyroscope, this kind of a setup. So as long as this gyroscope is spinning with the same speed, what happens is the torque remains fixed. And then because of that, it just keeps pointing in that direction, okay? So that helps. So we use this kind of, like technology, this knowledge, and the technology made from this knowledge to the, even in the exploring the space. So that is that. And I see there is something on the Zoom chat. So over here, what was the numbers? So final was final. So this is 2 and 4 times is yes. So omega f would have been 8, in this calculation, but looks like I just wrote 4. So if that's the case, then of course this is going to be, let's see, so let's see what happens in omega f, 64, IF, 1, and 32. Yes, so that gives us 32, looks like, okay? So we see there is different amount of energy over there. So these numbers, I just randomly put those numbers, okay? So they are not real numbers that is derived from the experiment. So that's why they are not even close. They're supposed to be actually close, okay, actually, but in this case, in this example, they are not. Okay, thank you for pointing that out, okay?
And we're
So now for your reference, it's here on my, slide, and it is also in the note, these things, okay? And by the way, I just added these pictures, and these pictures are also in the note, okay? And I think I have included, so this is also in the review slide that I just posted this morning. So if you open the another, like review for midterm 2 slide that I have posted, PDF version of that slide, you'll find this page over there as well. So basically what we just watched in the video is summarized here, okay? So this is going counterclockwise, so this is pointing up, okay? So angular velocity is pointing up. So when rotation is counterclockwise, omega is up and L is also up because, excuse me, they have same direction. Now, how about the angular acceleration and torque? Okay, they also have actual physical direction. So we know torque is I times alpha, so they have same direction. So in this case, it's saying up, or if we choose up as a positive, okay? So now to get the direction of torque, we need to figure out direction of angular acceleration. So acceleration, so to figure out direction of angular acceleration, if we recall how we figured the direction of acceleration is the same idea, okay? So for example, when V and A let's say when V is increasing in the direction of motion, so when V is increasing, A is in the same direction. When acceleration and velocity are in same direction, speed is increasing. So same thing happens for the angular rotation as well. When angular speed is increasing, when the spin rate is increasing, what happens? That means angular acceleration is in the same direction. So that's why when this is up, this alpha or angular acceleration is also up. And once you have the direction of angular acceleration, you also have the direction of torque. Okay. So in this case, torque is also acting in that direction. But if the speed is decreasing, see, it is still spinning in the same direction, right? So it is spinning in the same direction. Bicycle wheel, let's say, is spinning in that direction. And then you put your hand, let's say, a little bit, and it's slowing down. That means angular speed is decreasing. So speed decreasing means acceleration is in opposite direction. So that means it is now down. And so is the torque. So torque is now acting in the opposite direction of the angular velocity. So that's how we do it. And if it was rotating counterclockwise, for example, as I have shown here, this would be down, okay? And by the way, to get this, you start your hand with something like this, palm and the thumb is straight. Try to make this 90 degree, okay? And then now you are curling this in the direction of a rotation. So that's the two-step, right? First, second. So that is the direction of spin, and this is actually it's supposed to be straight up there, right? So that is the direction of angular velocity. Once you have direction of angular velocity and see if the velocity itself is increasing or decreasing, you can figure out the direction of acceleration, okay? And to emphasize that, I have added this one here as well. It's the same thing, right? So it is going that way. So that's why my, the fingers are in that direction. So thumb is pointing that way, means it's coming out. Okay, so that's what I'm writing here. So if it is on the plane of the paper, up means it's coming out of the plane. If your paper is sitting something like that, inclined, then still it's coming out of the paper. So that's another way to write the direction. Now, I'm hoping you can tell what if it is spinning clockwise, means if it was going that way, what would happen? So to grab that in the direction of spin rate, you have to turn your hand down like that, okay? So that's why thumb points down. So it's better if you have something round, even the water bottle, drink thingy, whatever it is, right? So for a moment, let me stop sharing it. So we may not have wheel all the time, but we always have something like this, all right? So think about it's spinning counterclockwise when looked from the up. So use right hand, not left hand, and grab it. And you see the finger is spinning in this direction and thumb is pointing up. Now, if you want to grab all the way around, you have to flip your hand and it goes like that. So it's down, okay? So practice that. So if you decide to take physics 2, you will be using this idea in physics 2 as well, okay? So let me share the slide back. So I have a couple of more slides here. So this is basically, I'm talking about, so this is from my note that I have provided you. So it's basically talking about the same thing I just talked about, okay? So if you think, you still need a little bit reading to fully understand, it is there, okay? Same idea. So here we are assuming up as a positive. And then there is this final slide, again from the note, okay? So this is basically generally that's how we figure out the direction of angular momentum, right? So now I could not find exactly this video the way I wanted to show you, or usually that's how I demonstrate in the class when I'm teaching in person. But the setup is something like that I found it, but this video does not describe the way I like to see it, but we can tell. So let's take a look. So at the beginning, just like, we watched a video where the student was sitting on a chair and holding a spinning wheel. So in that case, wheel was kind of horizontal, flat, right? But here, wheel is vertical. Oops. Wheel is vertical. And I'm saying, okay, it is, let's say, going something like that. Let's say, okay? If it is going something like that, if I curl my finger in that direction, I can tell the angular momentum is in this direction to the forward in the front part of this professor here who is doing the demo video. Okay, so the direction of angular momentum is front. How about direction of angular momentum in that direction then? Since nothing is spinning in this direction, here initially angular momentum is 0 in vertical direction. So this front means horizontal in this case, right? So this axle of this wheel is horizontal. So I'm pointing out of the page, and that's what I have written there, okay? Now, so initially the angular momentum in vertical direction is 0. Now, if you lift that wheel and bring on top of your head, just like it's being done, and remember it's rotating something like that. So now the angular momentum is up there for the wheel. So of course, I'm talking about wheel here, okay? So now, initially, total angular momentum is 0 along vertical direction. So notice here, total versus just the wheel. I'm talking about two things. Total initially is 0, but total seems to be not 0 here, or let's say there is an angular momentum in vertical direction now from the wheel. So now what we know is LF is Li, so that means has to be 0. Total final momentum has to be 0 because total initial momentum, let's say total here, is 0 vertically. So to make it 0, see there is this, So to make it 0, what has to happen? There has to be another angular momentum pointing down. And that comes from platform and portion. So if something is not spinning, if there is no angular speed, it does not have angular momentum. So to provide that angular momentum, to counter this angular momentum, it starts spinning in the opposite direction. So now the angular momentum here, this plus that, what happens? 0, because one is pointing up, another one is pointing down. Where is this pointing down angular momentum coming from? It is coming from the spinning platform and the portion. Okay. So see here, the angular momentum is conserved and the direction mattered. So the idea of this vector and their direction, it's not just a fancy things to talk about, but actually we need that to describe physical phenomenon, okay? So that is kind of important. So that concludes this chapter. So we're gonna take a break, and in the meantime, I'll also open the another, my PowerPoint slides. We're gonna go to the review mode. So we're gonna start from dynamics or Newton's laws of motion for circular motion, okay? So let's take a break for now, 5 minutes break.